As we continue in Euclidean geometry, we have another theorem called the Euclidean exterior angle theorem. We've already had an exterior angle theorem before we got to Euclidean geometry. It said something like this. You have a triangle and extend one of the lines. It says that the exterior angle is greater than both of the opposite interior angles. So it says that this angle is bigger than both of those two. Well, in Euclidean geometry, we know more than that. In Euclidean geometry, the measure of an exterior angle of a triangle is exactly equal to the sum of the measures of the two opposite interior angles. So this angle, the measure of this angle, is equal to the measure of this one plus the measure of that one. So the exterior angle of a triangle equals the sum of the measures of its two opposite interior angles. So I abbreviated opposite as OPP, interior as INT. So in this picture, this angle is equal to the measure of this is the measure of this angle plus the measure of that angle. Okay, well, let's take a look at this example. Given this following diagram, notice we have two lines cut by a transversal, actually cut by two transversals. Given the following diagram, if the measure of angle 1 is equal to the measure of angle 2, let me mark that. Let me make them look the same. So the measure of angle 1 and measure of angle 2 are the same, are equal. Must the measure of angle 3 be equal to the measure of angle 4? Let's justify our answer here for number 14. I'm going to tell you the answer is yes. And we'll show why. Okay, so, well, first, let me label this line L and this line M. We know that L is parallel to M. And why do we know that? Because these two angles are congruent. What property would that be? Well, let's see. If we do this, and we do this, we do that, that's property F. Remember that? L is parallel to M by property F. All right. Well, if they are parallel, if L and M are parallel, angle 3 has to be congruent to angle 4. Why is that? I'll go ahead and say that angle 3 is congruent to angle 4. So measure of angle 3 is equal to the measure of angle 4. By what reason? Because we know L and M are parallel. What property is this? What property says if you have two parallel lines cut by a transversal that these two angles are congruent? Corresponding angles on the same side of the transversal. That's property F. Notice we have on this one, the F looks like that, and on this one, the F looks like that. It's the same property by property F. And that justifies it. All right, now we have a corollary on basic Euclidean statements. All right, angle measures of a triangle sum to 180. The three interior angles, so to speak. Before we got to Euclidean geometry, do you remember what it was? It would be less than or equal to 180. Now it's going to be exactly equal to 180. The second one, acute angles of a right triangle. So what do we have there? Let's do, that's the right triangle. Acute angles are the other two. They're less than 90. And what do we know about these two? Well, just based upon this, if all of the angles add up to 180, and this right angle is 90, that means the two acute angles of the right angle will add up to 90. So that means they are complementary. So if you have a right triangle, the two angles that are not the right angle are going to add up to 90. Part C. The angle measures of a complex quadrilateral. That's a four-sided figure. What are they going to add up to? That angle, that angle, that angle, that angle. What will those four angles add up to? Well, if it's the same for all quadrilaterals, it'd be true for a square. And we know that the square is four right angles. So that's going to be 360. Or 360 degrees. I left off the degree symbols. And then remember what a Zachary quadrilateral is. That's one where you have right angles at the base, but this doesn't necessarily have right angles up here. But in Euclidean geometry, every Zachary quadrilateral is a rectangle, which means these will all be 90. All will be 90-degree angles. And then in Euclidean geometry, something that is not true with all geometries, squares do exist. We all know what a square looks like. 4 90-degree angles, 4 equal length sides. Okay, to finish up this video, we've got one more example. In this diagram here, we will assume that triangle ABC is an equilateral triangle. So let me mark something that tells us. If ABC is equilateral, I know this angle, I'll put it with 2 notches, this angle, and this angle, they're all equal to each other. In fact, they would all be 60 degrees. Okay, and we know that DE is perpendicular to BC. Okay, we've already marked that here. Must it be the case that ADF is isosceles? Must that be the case? It doesn't look like it, but then again, you don't trust diagrams. You only trust the marks you put in them like this to show these angles are the same, and this is a right angle. But you don't, and you trust numbers, but you don't trust the visual itself. Must this be ADF an isosceles triangle? Well, let's find out. And by the way, it's going to be yes. But we don't know that yet, so let's go show it. We know that angle B and angle C are congruent because they're in an equilateral triangle. And we know that the measure of angle D is equal to the measure of angle, let's see. We know that AD angle D, excuse me, and angle B, what do we know about those? Are angle D, this angle here, and angle B. Oh, we know that. Notice what they are. They are the two acute angles of a right triangle. So they add up to 90 degrees, so they are complementary. So the measure of angle B plus the measure of angle D will be 90. All right. The angle AFD, which maybe I'll put this 1, 2, 3, AFD, this angle, and EFC, those are congruent. Remember the reason? What do we call these? You can call them linear angles. Actually, no, vertical angles is what we called them. Vertical angles are congruent. Okay, and they are both complementary to angle C. They are complementary to angle C because if one of them is complementary to C, which it is, here's a right angle. So that means these two add up to 90. But this angle is equal to that angle, so this one plus angle C also adds up to 90. And since C and B have the same measure, they are congruent. They're also complementary to angle B. All right, well, what does that give us? Angle AFD and D are both complementary to angle C, as well as to angle B. So that tells us if they're both complementary to the same angle, that means that they are actually equal to each other. AFD and angle D are both complementary to angle C. So if two angles are complementary to the same angle, they must be congruent to each other. So angle AFD is congruent to angle D by theorem 12. That's what I just stated. They're both complementary to the same angle, so they must both be equivalent to each other. And that is the end of the proof.